Him.
I like that. Maybe I'll take one. That's all
What do
right.
you mean?
Yeah.
Oh, I should be in the picture.
Well, on yours, if you're gonna do that, would you show acceleration somewhere on your same diagram? If you have, that's now an elevator, do you put an A on the side of a vector?
I never draw acceleration arrows, and it's a matter of style. And I have no problem people that do that, especially use a different color or label it, that's fine.
Okay.
My style, I don't. I just do vectors. And I try not to get forces and velocities in the same diagram. In this one worksheet what we do, I ask you to draw a satellite going around orbit, draw forces, and then draw velocities. But be careful. How many of you have done this, or haven't done this yet? You've got a velocity vector and you've got a force vector, and then you take the resultant.
I'll give you the acceleration.
Hey, I did that when I first started teaching doing the sailboat. And I was stuck and I couldn't see where I was wrong. I had a velocity vector, I had a force vector, and I made my parallelogram really neat. And I didn't know it was wrong. I was a beginning teacher and I got all messed up. From then on in, and never put velocity vectors and force vectors on the same diagram, unless you maybe distinguish them dotted lines or better colored pencils.
Kids get really confused about where vectors should be placed. And so, to me, as long as you've got a consistent system that they can see.
Yeah.
And the thing is, it's nice to have all of the, for me at any rate, it's nice to have all the forces emanating from one central point. So that then when they start taking net force and stuff like that, they've got.
Oh,
Yeah.
there's a nice little rule that someone told me about a year ago about vectors, and the vector is on a diagram, has a fixed length and a fixed direction, but it does not have a fixed position. You can move it any way you want, as long as you don't, it doesn't have a fixed home.
That's right.
You can't stretch it or squish it or turn it around, but you
Yeah.
can move its position anywhere on the diagram. Students seem to be able to do that. And on an overhead projector, I have vector arrows cut out of cardboard, and I just move them all over
excellent.
the place on the diagram and say, well, what makes sense? Let's put them together up here or back over
And
there.
everywhere you put it, you'll end up with the same result.
That's right.
Put them any way you want, you'll always come up with the same displacement between where you started and where you end, no matter how you do it. That's a nice lesson. Yeah. Okay, let's get back to drawings, gang. All right, let's have a little girl hanging by some string, statics. A little girl hanging by a pulley. Remember little Susie Newton? Okay, hanging by the pulleys. Yeah, we'll draw a ceiling. And we'll draw, I'll do it here first and show you. There's a bar. What I'm doing is I got a pulley here. See that? Now I've got some strings coming down from the pulley. And I've got underneath the pulley a little girl. I'm going to be sure to make her head smaller than the pulley. I'll put some fingers here. 3's enough. Walt Disney taught us that. Her arms. Dress. And she's got a big smile on her face. And why does she have that smile on her face? Because she's in your class, okay? Yeah. And over here, maybe a little loose over here. And we might ask, what's the tension? What's the tension in the ropes that support the little girl? Go. Draw the ceiling. The strap. The pulley. And be sure that your strap, yeah, very good, Karen. Be sure that you can put your little axle at the center so it's not a cam. That just complicates things. Wouldn't change the answer, but nevertheless. Oh, some of you guys are fast. Good. The little fingers. The head beneath the vertical ropes, and I suggest you put the ropes first and then put the hands and everything. This turns out to be a challenge for students. But I draw and I say, let's pretend over here we have a little spring scale. And you just draw a little spring scale on there. And then you could say, what's the tension in the scale? How does the tension in the scale compare with her weight? And what's kind of a nice little touch is at the bottom of her fingers to show that the rope is a little loose, have it come out like this. See that? That's a little touch to show it's tight up here and loose over here. Just a little piece of rope coming out. Now, if we had a different pen, we could draw a vector diagram of all the forces that act on the girl. The girl is the system. Draw all the forces that act on the girl. get our vectors in the correct proportions. And I would make it so that these t's are half the size of mg. So here's a case where we're starting off with our center of gravity, but over here we put at the point of application. I think that's the way, I bet that's the way, that's the way you did it, Jim.
The application's over here, so you put these over here as the center of gravity.
For mg, I mean, how can you not put it where the center of gravity is? So we have here, and these vectors are, yeah, half the size of that, half the size. Hey gang, this is good. These are all correct. I like that. I really like that. Okay, how about a case of a little girl falls off a cliff and as she falls faster and faster, her acceleration does what? Gets less and less. So here's a little girl here. She's falling off a cliff. She's got her arms stretched out. Here's her fingers. Here's her fingers. Now she doesn't have a smile because she might be in your class, but she's in trouble. So she has a look of horror. And here's her hair like that. And up here is the cliff. She's just falling off. And down here is a big crocodile. Yeah. But here's a little girl, and here she's falling down, and you're going to put some weight vectors on her. But before we put some vectors on her, let's draw it. So again, the head, the dress, feet, arms out. Make the hair straight up because she's coming down, the hair's in the opposite direction. Now let's draw some vectors on her. She's accelerating.
Is that free fall?
Well, no, she's not in free fall because there's air drag there. And so her acceleration is, oh, let's call it 7 meters per second per second. Not 10, but 7. Now, if she's accelerating at more than half the rate at which she would free fall, how would you draw the air drag vector? Less than half or more than half per mg? No, if she's accelerating at 7 meters per second.
Oh, 7 meters per second.
Yeah. Would it be 7/10 or would it be 3/10? You want to have your vector 3/10 as long for air drag as here, right? Cutting it down a little bit. And if she accelerates at half g, then her drag would be half the rate. And these all look good. They all look good. Now here's a place where I haven't used any signs. If she's accelerating down, at this point I'd just say, well, she's going down. So I'd say she'll accelerate in this direction because W is bigger than R, boom, so W minus R. And I haven't got into a sign convention at this particular point, not with my non-science students. But they get the idea that there's a rule for this. As she falls faster and faster, R will get bigger and bigger. And pretty soon it'll get so big it'll cancel W, be canceled with W's in. And then the acceleration will be 0. I really, really lean on equations in my course. I think probably as much as any plugger and chugger does. Everything I tie to the equation, like sheet music. And the relationship is in these equations.
I think we're ready for the challenging one.
A person running. A person running. Yeah, running. Oh, hands and feet and everything, the whole 9 yards, all right? Let's see a person running. I'll do it up here quickly and I'll race it and we'll all do it together. All right, here's the head of a person running. Here's their body, leg, feet, other leg, feet, arm, other arm. Here they are. And maybe a little smile on the face. Why? Because they're in your class. Okay. So there's a guy running. Now, does it look like he's moving?
Yes.
It does, doesn't it? Okay. Now, there's a whole lot of going on there. But do you see anything do you see an element in there that makes it easy to follow from? It's all right angles. All right angles. See that? Everything's a right angle. Notice I've got the body tipped. in one of the little rules in cartooning, one rule is never draw a neck. You don't draw the neck. You draw as few parts of a person that you need, and to get the idea. And you'll notice a lot of, look at the Peanuts characters, nobody has a neck. What I'm going to do is I'm going to erase this and we're all going to do it together. Okay, let's do it all. It'll be slowly. We're going to do this slowly. Grab the head. Now the body coming down at an angle. 2 lines. Yeah, I'm tracing. I can tell you something about tracing. Sometime when you're doing a complicated drawing, I've done this. Go into class and draw it and erase it, but not quite all the way. Yeah, I've done this. Then you go in, it comes out this. Yeah. It's okay to cheat. You're in charge. Then the leg coming down, right angle. Now another right angle. Another right angle. Bottom of the pants. Let's just put the feet in last. This other leg extends. Comes up at a right angle. Draw the bottom of the pants. Now you can draw the cartoon feet. That's sort of like this. Sort of like Andy Capp. Andy Capp comic strip has that nicely. His foot is bent. That's fine, probably. Now the arms coming straight up. Right angle. It's okay, yeah, it's okay.
What are you thinking?
You can draw the hands is coming back like this.
Put the arms on.
Too much.
And the dust in the road. And then you have a person running. Now you're ready for your kinematics problems. Velocity, displacement, acceleration, whatever. Now I'll tell you what, you see how we have these so big like this? You know what, you probably won't draw one this big. I mean, I don't draw it that big on the board, but what I probably do is, now that you can do that, you might be talking about a problem of some kid that's running down the street, and you might want to just go like this. And then you start your problem. But you wouldn't take any more time than that, than you put a little vector. You might just do it like that, and that is enough. If you look at that carefully, it's terrible. But it's good enough. You're not giving an art class. Now, the last thing you want to do is to very carefully draw for a long time. It looks like you're teaching art rather than physics. So you just want to, you'll build up speed with these drawings as you do them. And when you can really do them fast, then you're right on. Speed's the name of the game. But you want to draw the correct proportions fast. And that's what we're learning to do today. In the teaching guide that I've talked about, or the instructor's manual for the college book, the first few pages of that teaching guide shows you how to draw these step by step. These ones that I'm doing here, they're right in that teaching guide. That's nice. Try the one, Susan. From this we can evolve to something very similar. A person throwing a rock. Maybe the problem about the Little League pitcher that's throwing the rock off the tower. He throws it horizontally, and so we got the 5 meter drop and so many distance out, and we get the speed. That's always a nice one. When we're talking about independence of motion, you want to assign that. Then you can follow it up with the tennis ball bit. But what we do there is just this. I draw the person, just like running. But with a little difference. This time I'll put the foot flat, And over here, I'll put the arm like that. Put a baseball cap on him. Put him on a tower. We call this 5 meters. Why are we using 5 meters for the ball to go out?
1 second.
Because it's the easiest one to do. And we want to make it easy. We want them to see how easy it is. And once they got it, we can take them along. But we'll start with 5 meters because it's a 1 second drop. But you see, it's the same figure, slightly modified. So let's try that. What you wouldn't want to do is draw the tower and then attempt to put the boy on the tower, because then his foot might not be in the right place. So draw the boy, then draw the tower underneath him. Little things like that you learn about. Now, if you did this about 10 times in a row before class, there's 10 flight drawings, and then erase them all. When that class is on, you'll draw it very quickly, very confidently, and very professionally. You're not a cartoonist, you're a physics teacher. Now, I want everyone to step aside and let's look at the artwork that we have. Now, these drawings are all about equal in terms of talent. So you guys should be putting drawings in your classes as often as I do. Someone swimming.
Running upstairs.
Oh, stairs.
Someone climbing upstairs?
Running upstairs.
Running upstairs? Let's do someone swimming first.
Okay. Swimming upstairs.
Nice spot.
Do both at the same time.
Good job, your guys.
I know, that's my first attempt, but I don't know.
Did you draw the head first?
Yeah, I would draw the head first, yeah. Now, this one I've never done, so with more practice, I might make it a little simpler. But the point is, you don't have to have too many lines there. And the simpler, the better, just like demos. Now, here's the test, gang. Here's the test. I have never done this one. And you guys haven't either. Now, compare the quality of the drawings. Many drawings in here more skillfully done than Paul's.
Stop it. Yeah, this is Pamela's color, the same, yeah.
I was just trying to draw the.
Johnny. I like that, Jose. I like that. Yeah. Jose's really a little frantic, isn't it?
Yeah.
Yeah, he's in Jose's class, yeah.
Now, we have a request for someone climbing stairs. I'll tell you what I wouldn't do. I wouldn't draw the stairs first. Draw the first one first. Yeah, put the stairs underneath.
Ah.
Huh.
Asking for that.
This is a very, very original one here.
Yeah, I see that.
Never seen that before.
See, once you can draw one thing, just keep drawing it. It's like guys that write one book and they keep writing the same book over and over again. Okay, you know the factor. There's a person climbing stairs, and it's our old friend, Mr. Right Angle. Same thing we've done before. I would like you all to become very, very confident at drawing this right angle person, because you can modify it for so many cases. Take the trouble to practice this at home or at school. Get that one figure down, and you'll do it all your life. Because you're developing a motor skill. It's about.
The outline of the body, see the curve.
You again? You again? No, erase it. I like it. I like it. I like it.
Jamaican man.
That was nice. That's nice. Let's draw that car going off the cliff with torques. I usually draw a convertible.
I usually draw a curve.
Draw what?
Or hers.
First. Oh.
Dead people going against 4 meters per second.
Okay, see, there's a car. Draw something like that.
You building wheels, right?
Yeah.
Oh, your car is moving, Jim. Hey, see Jim's wheels? Do you guys know why cartoonists started drawing wheels like this to show motion? Does anyone know why?
Isn't that what wheels do?
You've seen that with the ellipses? Well, it turns out the first cameras were slow. And when a car would go by, the shutter would come down, but show everything upside down, and show the wheel here, then the wheel here, da, 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 da. And it actually, the early photos really did show ellipses. And so it became, then the cartoonists picked it up and drew them leaning as we now see today. But this is a car at rest, the way I have it, or moving slowly, without the good Karen. Nice to see you. Nice. Now let's show the bit about a car goes off a cliff, and we want to tell our kids why it is that the car noses down. And we might draw the car first of all like this. It's ready to go off the cliff, and we'll draw all the forces that act on the car. Only 3. All the forces that act on the car.
At the top of the cliff?
No, and there it is. It's not going over the cliff yet. See how it's correct, just like yours, Brian. Now draw all the forces. There are 3: mg, and normal and normal. Okay, draw the normal a little differently, Jim. Draw the normal like you did with the elevator, starting at the wheels.
Okay.
And this would be more instructive. And I would draw it right like Guy has over here, right from the, it really is the floor pushing on the wheel. You draw it right down at the bottom. And then the sum of the forces in the y direction equal what? Sum of the forces in the x direction equal what? So it's either at rest or coasting at constant speed. And what's the net torque on the system? And now we can see the net torque is going to be 0, isn't it? The net torque about any point is going to be 0. Now I think you can see what happens when the car progresses and it's off the cliff. Now we have what? We have mg. But now we have all the weight on the back wheel. And none over here. We're going to get a torque. And it's going to rotate this way. And if the center of mass is here, it looks like there's a force that's tending to rotate the system clockwise. So if the front wheel leaves first, contrary to the film we saw, Speed, where the bus nosed up, if the front wheel leaves first, there'll be no support force here, and there'll be a torque that will tip the system. Then the system, of course, will then just, once it gets off the edge, once the body's rotating, it'll tend to rotate and might even crash upside down, depending on how far down you go. So if you wanted to not land upside down, would you go off in fast or slow? And let's suppose the cliff's about here. If you go off really fast, boom, you might tip just a little bit, clunk and go. If you go really slow, exaggerate. Okay. So how much it's going to tip is going to depend. How long is that torque going to act? And that torque over time will give you a change in angular weight.
Isn't it for the same amount of time?
Oh, no, if you go fast, there'll be a shorter time the torque will act. If you go slow, there'll be a longer time the torque will act.
But the torque's only while you're leaving the cliff, right? Okay.
Yeah.
Yeah, it's not time in the air, it's just time of leaving the cliff.
No, time that the torque is acting, yeah.
Right.
And the torque ceases to act, of course, when the normal force goes to 0. But there's some nice physics in there, and it's interesting. And you can relate to why is it that the toast always falls jelly side up.
Down.
And I've got to jelly side down. And I've got to read that book because there's some delicious stuff in there.
Yeah. How about the horse and cart, Paul?
Oh, that's a hardy.
Is it?
horse and cattle, I'll demonstrate it for you. We could try it.
Use
Try
the
it, Jane. Are you guys up to a real challenge? Yeah. All right. The horse and the cart. You get an A, you get this one.
Scout's honor?
Scout's honor. Okay, I'll draw a horse over here.
Horses are allowed to have necks?
Yeah, horse has neck.
It's like the horse that went into the bar, and the bartender said, "Why the long face?"
Yeah, right.
I don't get it either.
All horses have long faces.
You get something like that, that'll do it. And then the horse is, why is the horse smiling?
But it's in-
Because he has a long face, there we go. Something like that. Now, you see, it's, you notice in the videotape, it's a lot better. If you've seen the videotape, I go over, knock it right out. Guess what I did before class?
Practice.
I drew it on there and partially erased it. So in the videotape, you say, go like that. You know what I used to do when I used to first start teaching? I would go into class, like my class was 8 o'clock in the morning. I'd go in at 7:30 in the same room, and I was teaching Physics 4B. This was electricity and magnetism for calculus-based students. And what I would do is I'd have my lecture notes, and I would go through and do all my stuff, looking, make my little drawings, and go through the whole lecture that I'm going to do in maybe 15 minutes, what I'll do in 1 hour. And just do a dry run. I'm a brand new teacher. I want to be good. And I would do that, and then when I'm on, I could come in. It was a lot better than standing there going like this. Because you take a glance and you got it and you go. The name of the game is practice what you're going to do. And we all know that's the case with demos. You ever show a demo for the first time in front of your students?
Never.
Don't do that. The number of times it'll work out all right is so small. And the same thing here too, you guys. You can do this. You can practice a drawing that you know you're going to do beforehand. And you don't, it doesn't take long before you get it. And then you've got new tools
nice.
for teaching. I tell you what, everybody, you're all allowed, without humiliation from me, to do things like Chris is doing. Let's turn the creativity on now. I've been holding you people down for too long. The oppression is over.
Don't give it a face, whatever you do.
This is a hard one, though. This is a hard one. Now let's do a little physics game.
I want to jump over, please. No.
Let's let the horse and the cart be the system. Draw on your drawing the one vector that accelerates the system. Cart and horse are one system. Draw one vector that accelerates the system. And label it, yeah. One vector. The horse is pushing back on the ground.
Hunchback.
And it can't do that, can it? Unless the ground pushes on it. It's in that direction. Here we go right here again. There we have, the force is in the direction of motion, and that's the force that accelerates the system. The reaction to the horse pushing on the ground pushes on the horse.
Yeah, you got it.
One of my techniques in talking about Newton's third law, and I do it over and over and over again, and I don't think I do it too many times. I'll say, the horse can't do that unless, and then go to Newton's third law. The earth cannot pull on the moon. It can't do it unless the moon pulls back on the earth. The car can't push against the road. It can't do that unless, repeat. And then as to one on the other, use the one about what's the distance between Vancouver and Washington. How does that compare with the distance from Washington to Vancouver? And you see there's one distance with two arrows. And you have one interaction. And you talk about forces. That's the beauty of Newton's third law. One interaction with two forces equaling up. Okay, gang, I think that's probably about it, huh?
Yes.
Projectors where the lens folds out of the way. Sometimes all you need to do is take the little Phillips head screw off of here and then just crank this up and it'll come right off.
And what you see, of course, is the cone of light that you're getting as it's focused. So, focal point, see that? It's about there, isn't it? Where it's crossing over. So if you take some black paper, you can get this hot enough to burn.
Oh my.
Huh? Takes a while. See the smoke coming up? Now this is not the most powerful projector. So if you can get one that's got a good output, take that cover off, black paper, you can get a fire. So we've got a nice cup here, and we've placed it on our platform. You can see this is very high tech. Now, the big question is whether we can swing this thing all the way around in a circle. The other big question is which way should we be facing when we try the experiment? Okay. Now, it worked the other day with that penny, didn't it? So there's no reason why it shouldn't work today with a glass of water. It's no big deal. You want to see that again? Slow motion? Faster? Well, you've got to think about the minimum speed at which it's going to work, right?
Anecdote to that. I was in Turkey a few years ago.
Same in Greece, yeah.
People walking through the streets and carrying teas and cups of teas and whatnot. They're carrying a thing like that.
Yep.
It's not going to spill.
Little Greek thing.
But
Yeah.
carry it like this, my God.
Little Greek waiter. They don't care. They just go around the corner. It stays there. Doesn't matter. Why should it bother? It thinks up is whatever is perpendicular to the platform, and down is the way that it's sitting. Yep. Oh, you get a student to swing it. And they say, I want you to find the minimum speed at which you can still get around. We know that when we spin this little guy in a circle, something has to be pushing it inwards, and in this case it's the wall of this little hoop here. Now, if we, instead of the full circle, we take only part of the circle, take a little piece out, and ask ourselves the question, which path will the rolling ball follow when it leaves the ring? A, if it makes the curved path. B, if it goes in something like a straight line. C, if it sticks to the wall as it goes. And D, it depends on the speed. You could talk about this all kinds of times. I've done this right at the beginning of the chapter on inertia. And it's been a nice introduction to that. But there's so many other nice inertia demos, you know, with eggs flying all over the place in water, that you might want to save this for when you get into circular motion. So what do we reckon here? All us physics types should know that it's B, right? Body in motion tends to stay in motion unless there's something there to mess with it, right? Well, the thing that's there to mess with it is the wall of the hoop until the wall disappears. So there it goes. And if we do it at a different speed, there it goes. Doesn't matter. Now this then leads into the next question where you have your Nerf ball. So we swing this thing in a circle, and I'm standing here and I ask my students, okay, if I want to hit Fergus, where do I have to let go of the string? And what are they going to say? Yeah, some of them will say right there. Others will say, oh, it's going to sort of keep going a bit, so we, you know, so maybe just somewhere between here and here. But the physics types are going to say what? Right in front of me here, because that's the way that it's going at the instant that I let it go. So I want to let it go right there, not over here. If I let it go over here, I'm going to beam somebody up the back there. You ready? Okay, Fergus, open your mouth, Fergus. There we go. 3, 2, 1. Whoa! Close. I've seen other people, they have targets in the classroom pasted on the wall, and every group has one of these things, and you get points for whoever, you know, gets closest. There's 5 points if you hit the target, 4 if you're close, 3. They only get one shot at it, right? And they have to let go and stand in the right position. So they soon get the idea. It's kind of fun. If you slide your fingers together under a meter stick, where are they going to join together? In the middle, no matter what you do. And I need a volunteer. When we do the demo, do you want to be moving or stationary?
I'll be stationary.
Stationary, okay. I need one significant digit of yours. Can you just hold out one finger like that? Nice and horizontal. Corrie is not going to move her finger. All right, so instead of me doing this, I am going to be pushing. And I'm going to keep it horizontal. And let's see what happens. Stop pushing, Corrie. How did you do that?
Magic.
That's amazing. Why don't you reverse it, and I'll stay still this time, and you do the sliding. And we'll keep it horizontal. I'm not moving this. I'm not pushing. Go ahead.
That's kind of neat.
That's incredible. Now, wait a minute. It's got to be something to do with her fingers being stickier than my fingers or something like that. So let's replace your finger with a nice pen here, okay? Do you want to be the slider or the stationary person?
I'll be the slider.
You're going to be the slider. Okay, I'm not going to move.
Don't move, Peter.
How did you do that? Okay, maybe it's because this thing is perfectly symmetrical and it won't work with anything else. Let me see what else we got here. Ah ha ha ha. Ha 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 ha. Okay. Now where's the center of mass of this thing going to be? It's going to be close to here somewhere, isn't it? Ish.
There we go.
About there. So let's see what happens here. Okay. You're going to be the stationary or the pusher?
I'll be stationary.
Stationary. Okay. I'm going to. Ooh. 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 Oh, it looks like these coefficients of friction are different whether we're stationary or moving, doesn't it? And nature always seems to balance it for us. We'll try it with that. This won't work with a pen, will it? And a golf club? There's no way. You want to be stationary or a moving person?
I'll move.
You're going to move. Okay, I'm going to stand right here. I'm not going to move. No way. Uh-oh. Uh-oh. Uh-oh, we're in trouble. Uh-oh. Well done. Anybody got a nice, crisp donation to science? 50 would be good. 100 would be better.
Will American money work?
Merkin. Now this is kind of curvy, isn't it? See the shape of this? Whoops. So let's take some Canadian coin here. And what we're going to try to do is to get it to balance right on the edge of this thing. Now if you think about it, this is like a two-dimensional version of what we just did. Right? We're going to start off with this thing curved, like that. So that's what it looks like to start with. And we balance our coin on there. Okay, that's our starting point. And now we're going to try and straighten this out without toppling the coin. There we go. Straight. Same idea. I'm just a little, right? So it's not as perfect, but it's quite easy to do. Which one was yours, Paul? Was this the Canadian quarter or the US 20? Now, when you light a sparkler, and I'm going to use the propane torch to get this one going because it's fairly hefty, as you can see. When you light a sparkler, the stuff that's coming off is very hot or medium hot or cold, or what do you reckon?
Very hot.
What about the temperature of those little sparks coming off there? They're white hot, aren't they? Yeah? That's really, really high temperature. So if one of those was to land on my skin, well, I don't think so. So how come it doesn't hurt? It's an incredibly high temperature. It's way hotter than anything that we're going to get in that propane flame over there. There's a lot of temperature, but not much heat. Not much heat. A lot of temperature, but not much heat. Make the same distinction when you're talking about potential, electric potential, and potential energy. you can have very, very high voltage, but if you don't have much charge at that high potential, you're not looking at a lot of electrical energy. And here, you've got a very, very high temperature, but you've got a tiny amount of material at that high temperature, so you're not looking at a lot of heat energy. So that way you can distinguish between the two. We were talking this morning about color, right? And this is an exercise in recognizing your colors. You see on the screen a bunch of colored words. We're going to read the words starting at the top left and working our way across. And we're going to read them out loud, okay? So we're going to start with what? Green, red, blue, yellow. Faster. 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 Excellent. That wasn't too tricky. Now what I want you to do is, instead of reading out the word, I want you to say the color in which the word is written. So we'll start with black, green, red. Come on. Faster, faster. Come on, come on. You guys don't know your colors or what? It's not that hard. You can put a 3-year-old up here. They could do that. So what's the problem? We've learned how to read. That's the problem. And once this, thing in here, this little computer, whatever it is, knows how to read, it's very hard to unread. Would it help if we did it upside down, do you think? You want to give it a shot? You ready? Green, purple, black. Hopeless. Hopeless. You know what? All we proved is that you can read upside down. Is that going to help? Turns out nothing helps. You can take it out of focus. You can do all if you put it in an unrecognizable alphabet, Cyrillic, Greek, whatever, then you could do it. And you bring a little 3-year-old in, knows the colors, doesn't know how to read, it's a snap. What's the big problem? But once your brain has learned how to read, very hard to unlearn. Okay, so we've had the 2 minutes of ritual humiliation with which we like to start all of these events. We're going to look at weight and forces and tension, tightness, stretching. And I got a kilogram here. And if you're familiar with the metric system, and you're looking on a scale in which the forces are expressed in units called newtons, then my question is, what will the scale read when it's suspended, when it's a kilogram is suspended from it? We would expect this to be about 10 newtons. Here at the surface of the planet where we live, gravity is pulling down on every kilogram with a force of about 10 newtons. And we talk about the Earth's gravitational field strength. Look at that. Boy, gravity. Talk about the strength of the Earth's gravitational field is about 10 newtons on each kilogram. Now, the little rig that I've got here is designed for my classroom. It's obviously a very small scale, and I can't use these great big scales on it. But I do have a smaller version, and you can see that this is expressed in newtons there. So if I pick up 1 kilogram on this scale, what should we see? 10 newtons, just the same as the other scale. Spring is being stretched. Does it make any difference if instead of hanging the kilogram right on the scale, I attach it to a piece of string like that? Is it still going to read 10 newtons? Yes. Yeah, if we're assuming the string isn't adding any extra weight, it should still be the same. 10 newtons, and there it is, about halfway down, 10 newtons. Does it make any difference if instead of holding the top of the spring directly, I hold this piece of string like this? It's going to be exactly the same thing, isn't it? Still in the middle of the range, about 10 newtons. Does it make any difference if I suspend it from a 1 kilogram mass. Like that. Instead of having my finger in that loop of string, I've now got a kilogram, which I'm holding up. So we should still see about 10 newtons. Does it make any difference if I turn it around and hold it like that? Doesn't seem to, does it? We're still holding up the weight of the same kilogram. These kilograms are equal. Does it make any difference if we suspend the kilograms over the edge of our little platform here? Check your neighbors and see what they think. Now, obviously with your class, you'd then take this further, let them think about it, and then just before you show them the answer, guess what? It's lunchtime, or it's recess, or it's the end of the day, or whatever. So you let them go home and think about it. Now, should we do that? You want to see it? Oh, I don't know. I think I'll see how good you are for the rest of the session before we actually come back to that one. Okay. One of the practice sheets that we had this week was little Nellie Newton. And little Nellie Newton was hanging from a clothesline. And we were asked which side of the clothesline was most liable to break under her weight. If instead of being at an angle like this, the ropes were like this, each one of them would have to be supporting how much of her weight? Half and half. See that? So here we've got 2 scales. What was the weight of this kilogram? Anyone remember? 10 newtons. So each one should read about 5. There's that one. There's that one. About half and half. Nice and vertical. When we get away from the vertical, though, we still have to provide a total of 10 newtons of lift. And if we're not pulling directly upwards, that means that we have to increase the force that acts. So that each of these, are they roughly equal? That means I'm holding them at about the same angle from a vertical line right through the middle. So they share equally. But what if we change it so that this one is a little steeper? You notice what happens? Are they still equal? Which is bigger? The one which is closer to the, starts with a V, rhymes with vertical? Vertical, you got it. The one that's closest to the vertical will support most of the weight. And so if we go over this side, guess what? Huh? See that? So which side of the clothesline has got more tension in it right now? Which part of the clothesline is tighter? Now we can do some other stuff with this. Here's our scale. Does it read 0, by the way? Okay. Here's our kilogram. What's it going to read? 10 newtons. There's little Nellie Newton. She's just lost a lot of weight. But here she is. Let's see what happens when we have 2 scales supporting her weight. At the moment, both of these read 0. Am I right? Okay. We're going to join them with a massless rod. A massless rod you can buy at the same place that you get those frictionless pulleys, etc. And if I place these over the scales, no peeky, and we put our weight right in the middle, check your neighbors and see what you think each scale is going to read. Now, what if we move it to one side or the other? If we move this over here, what's the happy face going to be? Is it going to be 5, less than 5, more than 5? Let's take a look and see what it is. Can we read that? It's about 9? Okay. There are some people in here who can now predict what the other scale has to read. Maybe you're sitting next to one of them. Why don't you check? About 1-ish? Because they have to add up to a total of 10. If we move this guy over here, what happens to this one? Goes down. What's it down to now? 2, so this should be about 8. No big mystery there. But now, gets a little bit more interesting. Unfortunately, this is not a massless scale. But we can calibrate the upper scale so that it ignores the weight of the lower scale. So right now they should both be reading 0. We're going to put our kilogram on there. And I'd like you to talk to your neighbors and discuss what we should see on these scale readings. If I had to hold this thing up like that, how hard must I be lifting this to keep it where it is? I've got to be pulling up with a force of 10 newtons, just the same as the gravity pulling down. So instead of my finger supplying the 10 newtons, this spring is supplying how much? 10 newtons. And what should this scale read if it's got a 1 kilogram mass hanging on the bottom? 10 newtons. So it kind of makes sense, doesn't it? Let's see. There's one. There's the other. Now, we're going to change the rules a little bit here. Instead of having gravity stretch our springs, we're going to put a piece of string on the bottom here and tighten it until we have a reading of 10 newtons, which is about there. What should the top scale be reading right now? Is it still 10 newtons, you think? I think it should be. Let's check. This one says almost 10. This one says almost 10. Same. Now, if 1 kilogram weighs 10 newtons, then how much would half a kilogram weigh? 5 newtons. How about 1/10 of a kilogram? 1 newton. How about 4/10 of a kilogram? 4 newtons. Piece of string here, 200 grams, 200 grams. I'm going to put this on the bottom here of the springs. And I'd like you to check with your neighbors and see if you can tell us what's happening. Will the reading still be 10 and 10? Yeah? What was providing the 10 newtons of force before we hung these weights on there? This string. It was being pulled by the string, which was tight. We've let gravity take over some of that. So the string doesn't have to pull as much. If we've got 4 newtons of weight here, how many newtons of tension in this piece of string down here? Anyone guess? About 6. So we've still got 10 newtons provided by the 4 newtons of weight and the 6 newtons of tension in the string. Well, that's not too bad. How much could we put on there before we'll change the reading on the scale, do you think? More than 10, we're going to stretch it more than the string is tightening it down. Well, let's make this a little bit more interesting. Let's put our 4 newtons on the middle scale now. I think we should put that on the piano with the other one and let you guys think about that one. This morning we were talking about light and reflection. And I don't know about you, but when I was a kid, mirrors always bothered me a little bit, not simply because of the way that I looked in them, but I always wondered why it was that a mirror will turn the picture left and right, but it won't turn the picture up and down. How does the mirror know the difference between horizontal and vertical? And then someone, a few years ago at an American Association of Physics teachers meeting, showed, and I forget who it was, I wish I could remember, showed me a way around that. And what he said was, don't think that the mirror is turning your image around. What the mirror is showing you is a picture of you facing in the opposite direction. And isn't that right? That's my right. It's your left, because you're facing in the opposite direction. Now you're going to be my image, and whatever I do, you do. Okay, so if you want to stand over there, we're going to pretend there's a big mirror here. Big vertical mirror. And if I'm standing like this, is she okay now? Oh, this is cool. Okay, this is very good. Very good. All right. Okay. Oh, she's good. She's good. You see how it's just the other way? Right? Okay. Come on. Now. Thank you. Thanks, Joanne. But isn't that what the mirror is doing? It's just giving you a picture. Now, in the movies, in the submarine, up periscope, and they want to scan the horizon for the enemy. Now, what does the captain have to do to look all around the horizon? They actually turn, don't they? Yeah, so why don't they just have something that the captain can stand there and the top just sort of swivels, hang on, and the top just swivels around while he's looking in there? Wouldn't that be easier? Get a little motor on there? Why don't they do that? I'm going to pass this around. This is just plumbing fixture stuff, right? With a piece of plastic mirror glued and taped on the back. There's high tech, there's low tech, Aztec, it's just store stuff. And just try that. See if you can look through. Okay, how does the room look? Okay, that's fine. Then turn it around like that. Ooh, that's interesting. And then turn it like that and look through. Oh my, that hurts my brain. Okay, we're going to start over on this side because you guys haven't had a chance to have it start here. Acceleration is a vector. And to show that, here's my acceleration board. I've got a right angle triangle. See that? And there's little screws. And I've got nylon fishing line, fairly tight along the sides. There's the red side here, green side here, black side here. And I've got little 1/4-inch hex nuts which can slide down and hit that screw at the bottom. This is the vertical one. This is the one on the long side of the triangle. This is the one on the short side. There's a little bit of friction there. It's not too bad. Now, what we can do, we know the relationship between those distances. If we say that the long side is d, top angle is theta, bottom angle is alpha, this is d cosine theta, this is d cosine alpha. But if acceleration is a vector, the acceleration of the little hex nut down the vertical is going to be g, acceleration due to gravity. Over here it's going to be diluted a little bit, g cosine theta. Over here, g cosine alpha. Since distance starting from rest is a function of 1/2 the acceleration times the time squared, solve for time. T1 is 2d over g. T2 is 2d cosine theta over g cosine theta. Guess what? The cosine thetas disappear. Same thing happens to the cosine alphas. So if we have all three of these ready to go at the same time. Now we're going to make sure the board is vertical. And we're going to let them go at exactly the same time. And if acceleration is a vector and we've treated it the right way, what should we hear? They should all hit once, shouldn't they? 1, 2, 3. Pretty close, right? I'm going to do some laser things now. There's a fellow by the name of Herb Gottlieb. And he does some wonderful things at teachers' conferences involving metrologic lasers. And I've picked up lots of tips from him over the years. I'm going to start with looking at reflection very briefly. We've got 2 or 3 lasers here. And what we need at this point is a volunteer. And who's got steady hands? Nobody will admit to that, eh? I need a volunteer with a steady hand. Close your eyes. Okay. We should be, yeah, we're up on the, see we're up on the wall there, that spot? Okay. So does anybody have steady hands here? Gary, okay, I'm going to give you a little mirror. And Gary's going to go up there and catch that spot and reflect it straight back to the laser for me.
You bet.
Okay, you want to try to get it straight back to the laser. And I'll give you a little screen here that you can hit. You're not, yeah, you're catching it pretty good. Can you hit that piece of paper? Yeah, that's pretty good.
I can't see where I've got.
Can you hold it steady, Gary, please? Now, if Gary can hold it steady, then what does that tell us? That Gary is dead. All right? So that's good evidence. Thanks, Gary. But I'm going to give you something else. This is a total internal reflection block. It's taken from a piece of surveying equipment. And what the light's going to do now is behave a little bit differently as it reflects. So Gary's going to do the same thing for us. There you go. There you go. Now, just twist it a little bit. Does it matter?
Actually, I can see little orange spots coming up at
Yeah, it's hitting your hand rather than the...
Oh, yeah.
There you go. That's better. Doesn't matter what he does.
What are the little orange spots? Is that interference?
Yeah.
In the beam, though. I see in the beam.
That's probably just chalk dust.
Okay.
Yeah. So that retroreflector, because it's going to go in across the corner of the box and back, total internal reflection happening twice, always going to come back parallel. So when the guys that were up on the moon, they left reflectors there so that people on Earth could bounce laser light up and check that distance. Do you think they use little plane mirrors, or do you think they use retroreflectors like that one? Like that one. Phone your local land surveyors and just ask if they've got any of these retroreflectors that have been run over by a D9 or something recently. And that's how I got that. They mount them 3 to a triangular plate. Thanks, Gary. And this one was damaged, so they just gave it to me. And I gave 2 away to other physics teachers, and I kept this one myself. So that's very, very handy. It's a nice example of total internal reflection. And if you look at the shape of the little prisms that make up a bicycle reflector or the reflective lights on the back of your car, guess what's behind that nice smooth surface? Little corners, little 3-dimensional corners of a box for the total internal reflection to go in and come back. Instead of having this kilogram hanging here, I'm going to pound a nail in here. How hard would the nail have to be pulling to support this kilogram? 10 newtons. So is there any difference between the nail providing the 10 newtons and good old gravity providing that 10 newtons? I don't think so. 10 newtons. Okay? Remember when we had the 4 newtons on the bottom? It reduced the tension below there by how much? 4, wasn't it? Did the string get any shorter? No. It got a little bit less tight, but it didn't get smaller or longer. But now, when we've got our extra 4 newtons up here, we've reduced the tension below here now, haven't we? So there's less tension through here. But this is a spring scale. And when a spring scale loses tension, what does it do? Does it stay the same length? Does it get shorter? Does it get longer? Shorter. A little bit shorter with less pulling force. But this is fixed at the bottom and fixed at the top. So if this scale has got a little bit shorter, did the string get longer? If the string didn't get longer, what must have got longer? The top scale. How will the extra length of the top scale compare to the shortening of the bottom scale? Same. That corresponds to the same increase in length here as the decrease in length there. And if these springs are the same as each other, same change in length corresponds to the same change in tension. So whatever the change is down here, there'll be an equal change, but in the opposite way up here. Now we said this was getting smaller, didn't we? So this must be getting bigger. The total difference is 4 newtons. How do you divide that equally? One's going to increase by 2, one's going to decrease by 2. This is going to get tighter by 2 newtons. This is going to get a little bit less tight by 2. They used to read 10 and 10. Anybody want to predict what this one reads? 12. Oh! And this bottom one is now going to read 8. Let's look. That was 12. Is this one 8? There it is. 8 and 12. Ah, yeah. Come on. Well done. Thank you very much.